Within Chapter 4, we're looking at reactions that take place in aqueous solutions. That means in water. An important question that we're going to ask again and again is, what's in the beaker? What particles are in the beaker after the substance dissolves? We're going to begin by looking at what's in the beaker and classifying the substances as whether they are strong, weak, or non-electrolytes. That's introduced in section 4.1, General Properties of Aqueous Solutions. We can begin by asking the question, well, what is the difference between an electrolyte and a non-electrolyte? What would be examples of each, and how might an experiment be used to classify them? Looking within the e-text, it says that a substance such as NaCl, whose aqueous solutions contains ions, that's an electrolyte. And a substance like sugar that does not form ions in solution, that's a non-electrolyte. So in a way, a conductivity probe, that is a free ion detector. When the light goes on, it means that we have ions that are freely moving about the solution. And that can be used to classify the substance as an electrolyte or a non-electrolyte. When sodium chloride solid is dissolved in water, the resulting aqueous solution is one that gives us ions that are free to move around of the sodium and the chloride. When we add sugar, it could be dissolved in water. We can make a sugar water solution out of it, but that remains as molecules. It's aqueous now, but we don't have any free ions. The sodium chloride is an example of an electrolyte. It's an ionic compound, and the sugar is a non-electrolyte. It's a molecular one. That classification of thinking about ionic compounds versus molecular ones is something that we're going to build on. Let's look at a illustration of this. So we can add a conductivity probe to this container of water. If we begin by adding sugar to it, the sugar will dissolve. The conductivity probe is not going on. We don't have any free ions within that solution. Switch it to salt. It's trying to show us that the light bulb begins to go on. The conductivity probe is telling us that we have free ions that can move around when we add the salt to the water. Looking more closely at the particle level, if we add sodium chloride to water, notice how when it dissolves, the ions move apart and we have free ions in solution. This would be a strong electrolyte. Adding sugar, the sugar will still dissolve, but the molecules are moving apart and we're not having ions produced. Again, that's what the conductivity probe is telling us, whether we have free ions or not. Let's test a few different samples. When we add sodium chloride, notice how it breaks apart and gives me sodium ions and chloride ions in a 1-to-1 ratio. When we add sucrose, no ions present, it still remains as a molecule. How about calcium chloride? Ionic compound. Ions are produced. It's in a 1-to-2 ratio because for every 1 calcium, I have 2 chlorides within the formula. How about sodium nitrate? Ionic compound. Produces ions in a 1-to-1 ratio. And I see that that polyatomic anion, the nitrate, stays together. Cations and anions in solution. Strong electrolyte. Sucrose is a sugar. It's molecular. It dissociates, gives me molecules. Glucose, that's another sugar, molecular. No ions in solution. These would both be non-electrolytes. This prompt says equation 4.1 shows arrows pointing left and right, whereas in 4.2, we have an arrow just pointing in one direction. Here are those equations, 4.1 and 4.2. And this is what it means when it says arrows pointing in both directions versus just one direction. What do they mean? The E-text tells us that these arrows pointing in both directions means that the reaction is significant in both directions. At any given moment, we have the molecules ionizing to form the ions, and then some of the ions recombining to form the molecules. That's not taking place with the HCl. The arrow pointing only in one direction tells us that the particular ions, once they form, are not going back to form the molecule. Now, these are acids that we've seen before. Equation 4.1 is describing acetic acid, forming the acetate ion. And the bottom one, 4.2, is hydrochloric acid, forming H plus in the chloride ion. Acetic acid is a weak electrolyte. It is not giving me entirely ions in solution. There are some molecules present due to this back and forth. HCl, it is a strong electrolyte. The arrow going only in one direction tells me that I'm only having ions formed. Some molecular compounds, like HCl, are strong electrolytes. Others, like acetic acid, are weak electrolytes. Sample exercise 4.1 is an important idea because it's asking, well, what's in the beaker? It says the accompanying diagram represents an aqueous solution. All of the choices listed are ionic compounds. Ionic compounds are going to be strong electrolytes. If we think about how they dissociate, MgCl2 is going to dissociate to give me ions that are in a 2-to-1 ratio. 2 chloride for every 1 magnesium. Potassium chloride, potassium sulfate, how do they dissociate? What's in the beaker? Potassium chloride dissociates 1-to-1. Potassium sulfate dissociates 2-to-1. I have 2 potassium ions for every 1 sulfate. I'm keeping the polyatomic there together. I think that this diagram then best represents the potassium sulfate solution. I see +1 cations, I see -2 anions, and the cation to anion ratio is 2-to-1. So we're able to make predictions now as far as whether something is a strong electrolyte, non-electrolyte. As we begin to classify them, are we looking at ionic compounds or molecular ones? The types of predictions then lead to particle level descriptions. If we look down to the next section, we get a little bit more data that we're going to have to begin to interpret. And this involves looking at precipitation reactions. The table here is something that's provided on exams. And it can be used to think about and predict precipitation reactions. The image here shows a precipitation reaction. We have ions in one beaker, ions in the second beaker. They're combined, and we now see that a solid is forming. Ionic compounds we described as strong electrolytes, but that doesn't mean they have the same degree of solubility. This is first adding sodium chloride to the water. We add some sodium chloride, it dissolves. We see that we have sodium ions and chloride ions. They're in a 1-to-1 ratio. We add more of the sodium chloride, it dissolves. We add even more, it dissolves. Sodium chloride is a very soluble ionic compound. We can keep adding it, and it keeps dissolving. Can we add an infinite amount of sodium chloride solid? That seems unlikely. If we look closely, we see some sodium chloride existing here at the bottom of the container. We've added a lot of it, and some of it now remains. If we add more sodium chloride to it, we see that the total amount at the bottom has increased. So a lot of sodium chloride will dissolve. It's quite soluble, but not an infinite amount. Here's strontium phosphate. Ionic compound, we add it, it dissolves. We add a little bit more. Okay, we already have it now sitting at the bottom of the beaker. This is an ionic compound. It's a strong electrolyte, but it's not as soluble as sodium chloride. Silver bromide, let's test that. We add some, it dissolves. It's in a 1-to-1 ratio. We add even more. Okay, it looks like I now have some solids sitting in the bottom of the beaker on this one. So this is not nearly as soluble as the sodium chloride. So these are all ionic compounds, but they have differences in terms of how soluble they are. That's what this table here is summarizing. We're not going to have that simulation on an exam, but we will have this table, so we need to be able to interpret it. It says, based on table 4.1, is the sodium chloride a soluble ionic compound or an insoluble? The way we read this, soluble ionic compounds are listed at the top based on their anions, insoluble at the bottom. So if I were to find sodium chloride, the chloride ion leads to soluble ionic compounds. There are some exceptions that would make it insoluble, but sodium is not one of those exceptions. So I read this to say that sodium chloride is a soluble ionic compound. How about the strontium phosphate? If I find the phosphate, that's listed as being insoluble. There are some exceptions, but strontium's not one of them. So it's in the category then of an insoluble ionic compound. Let's do the same thing with silver bromide. The simulation said that it would have poor solubility. I find the bromide ion up here in the category of soluble ionic compounds, but it has poor solubility because it's one of the exceptions. Exceptions turning the soluble into something that would have poor solubility. So that's relatively insoluble. Let's see how this then applies if we're looking at a precipitation reaction. Predict the identity of the precipitate that forms when we combine barium chloride and potassium sulfate. First thought is chlorides are soluble, sulfates are soluble. So when I add those initial solutions, they're giving me ions in the beaker. Let's look at the various combinations now and see if we have a new combination that leads to an insoluble substance. How about the potassium with the chloride? Chlorides are quite soluble, including those with potassium, so I'm not going to have a precipitate form. How about the other combination? Barium with sulfate. Sulfates are usually soluble, but I see barium listed as an exception. This means that when I put it together, the barium sulfate would form a solid, a precipitate would form. If we were to write the balanced equation, combining solutions of barium chloride and potassium sulfate will give me potassium chloride and then the solid barium sulfate, and I can balance that. We can look at these types of equations in different ways. So if we were to write the overall balanced equation, I show it here. One thing we can do then is to think about these aqueous strong electrolytes. Even though it's written as being BaCl2O aqueous, we've described how they're really not together, meaning that when they dissociate, we get the ions in solution. So let's take and break apart all of the aqueous strong electrolytes. Barium chloride, if we break that apart, I would have barium ions and chloride ions. Potassium sulfate, aqueous strong electrolyte. Let's break that apart. Potassium chloride, aqueous strong electrolyte. Let's break that apart. The final one, barium sulfate, that's a solid. That's not aqueous, so I'm going to keep it listed there, written as a solid. This is the full ionic equation. It's telling me everything that's in the beaker before and after the reaction. Now what we can do is we can identify what are called spectator ions. Spectator ions are ones that are in the beaker both before and after the reaction. So I would initially have chloride in the beaker beforehand, chloride aqueous, and after the reaction takes place, I still have chloride aqueous in the beaker. Similar scenario for the potassium. Potassium ions were floating around in the beaker before the reaction and after. So both the potassium ions and the chloride ions, they're spectators. They're watching the reaction take place, but they're not participating in it. If we cancel those out, we're left with what's called the net ionic equation. So we had spectator ions in the beaker, but what was participating in the reaction were barium ions, sulfate ions, combining to form the solid barium sulfate. That's what's called the net ionic equation. The last part, section 4.3, we begin to look at acids and bases. What are acids and bases? And how do they connect to these descriptions of strong, weak, and non-electrolytes? That's what we want to figure out. So an acid, when it is added to water, it produces H plus aqueous. A base, when added to water, produces hydroxide aqueous. We've seen earlier in this video a few examples. Hydrochloric acid produces H plus. Acetic acid produces H plus. Hydrochloric acid is a strong acid. It is a strong electrolyte. That's what the arrow going in just one direction tells me. Acetic acid, however, is a weak acid. It is a weak electrolyte. When I add acetic acid to the beaker, I have a combination of molecules and the ions present. How about the bases? Sodium hydroxide, that's an example of a strong base. It's an ionic compound, a strong electrolyte, and it produces hydroxide in the beaker. Ammonia, that's an example of a base, but if I look at the formula, I don't see any hydroxide listed. That's because the ammonia reacts with the water. We have these arrows going back and forth as it's producing the ammonium ion and hydroxide. The back and forth arrows, this is indicating this is a weak base and a weak electrolyte. Table 4.2 lists some common strong acids and strong bases. It's going to be best if we memorize the strong acids. I see 1, 2, 3, 4, 5, 6, 7 of those listed. Memorize the strong acids. For the strong bases, all of these are ionic compounds. All of these have a hydroxide in the formula. And based on the periodic table, they're all from the first or second column, the alkali or the alkaline earth. So to summarize all of these different relationships, we have strong, weak, and non-electrolytes. We've also introduced the term acid and base. Ionic compounds that are always strong electrolytes. Similarly, strong acids are strong electrolytes. Examples we saw were sodium chloride and hydrochloric acid. We saw that we have a weak electrolyte if it's a weak acid, with acetic acid being an example. And also, a weak base was a weak electrolyte, with ammonia being an example. If we go back up there to the ionic compounds, other ones to consider would be zinc nitrate, strontium hydroxide. The zinc nitrate is a good example because it's including this polyatomic anion, the nitrate, and we want to think about how the entire polyatomic remains together when the ionic compound dissolves. Strontium hydroxide is being chosen because it's an ionic compound, strong electrolyte, and it's also a strong base. For the strong acids, there's 7 of those that we want to memorize. Hydrochloric acid is an example. HNO3, nitric acid, is an example. Notice, just like we saw previously for the ionic compound, that the polyatomic, the nitrate, is remaining together. For the sulfuric acid, when it says first proton, what it means is it's a strong acid in terms of having an arrow pointing in just one direction, with the H2SO4 donating one of the protons to the solution. That's what it means when it says sulfuric acid is a strong acid for the first proton. When it comes to the weak acids, well, there are thousands of weak acids. So how do you determine if something is a strong acid or a weak acid? Memorize the strong ones. Memorize the strong ones, and if it's an acid that's not listed there, it must be a weak acid. We're going to encounter acetic acid quite often as a weak acid. Also HF. HF is another important one to remember. Arrows going both directions. It's a weak acid. It's a weak electrolyte. When it comes to the weak bases, there are thousands of weak bases. How do we identify them? Well, if we can identify the strong bases, then anything that's a base that is not listed as a strong base must be a weak base. Finally, for non-electrolytes, I'm looking for molecular substances. They're not going to be acids or bases. Sugars like sucrose would be an example. CH4 methane, that would be another example. So in this overview here, we've covered a lot of ground. We classified solutions as having strong, weak, or non-electrolytes. We saw how that was related to precipitation reactions. And we began section 4.3, where we now saw how we had examples there of acids and bases that could also be classified using this description of strong or weak electrolytes. Within class, then, you're going to seek to apply these ideas.